Hi, Joe. Nice to meet you. How are you doing today?
Hi, Kwabena. I'm doing just great out here in the snowy Northeast. We've been
Snowy
having
Northeast.
quite a winter here.
Ah, gotcha. Yeah, it was just raining super heavily in San Francisco. Umbrellas were inverting and things like that. That's February for you. So, Joe,
Yeah,
you work at
tis the
Everspin,
season.
and you're the senior director of marketing there?
That's correct. Yeah, yeah. And so with that, let me just tell you a little bit about Everspin Technologies.
Mm-hmm.
We are a company based in Arizona. Our
Mm-hmm.
headquarters are in Chandler, outside of Phoenix. And I happen to work remotely, which is the New York connection you heard. And we're a company that specializes in the commercial development and shipment of MRAM technology. And MRAM itself is a new type of memory technology uh, in the sense of relative to the other standard commodities that are out there, new. And it stands for magnetoresistive. And we use that property to basically establish a way to take a magnetic state of high resistance or low resistance into a data state of a 1 or a 0.
Mm-hmm.
And it's essentially the difference that we make is that we store the data as a magnetic state as opposed to electrical charge that you see in most other memories.
Mm-hmm.
And the nice thing about that is that number one, magnetics is persistent. It doesn't go away when the power is turned off. It can be switched very quickly. And it doesn't have the typical wear out mechanisms that you have associated with other types of non-volatile memories.
Mm-hmm.
And so therefore you get the kind of the benefits of RAM-like speeds along with non-volatility that you get with technologies such as flash. And it's that combination of things that we put together that help us deliver a very unique value proposition to the marketplace here.
Mm-hmm. Is this like core memory from back in the 60s that helped, build the moon lander and the Apollo
In
mission?
the sense that we both use magnetics.
Just a lot more dense.
Absolutely. Yeah, but now you've gotten into solid state, and as opposed to just a magnetic state, we use a magnetoresistive state,
Mm-hmm.
which is where the resistance comes in, which allows us to use it in our electrical processing like a standard CMOS technology.
Mm-hmm. And I heard you mention you have some slides that you want to show about this technology and such and what Everspin is building.
Yeah, I've got a couple things just to further expand upon, what it is that's unique about the product, what applications it fits in, and hopefully that will then lead into the exciting things that you're doing and how the two can come together. So let
Thank you.
me put that up here. Let me know when that's coming through. I think I see it myself, don't I? Yep.
Yeah, I got it. Everspin Technologies.
All right, good. So that's us.
Mm-hmm.
And so let me get it back up to the top here. Yeah. That one really quick. Sorry. So we've been in business for about 16 years now. We've shipped hundreds of millions of products to the marketplace. So to call it an emerging technology is really not quite accurate anymore. It's really been pretty well established. Although I will say still kind of a niche technology relative to the size of other memory markets. And we spun out of NXP. Originally actually Motorola and Freescale, and now it's NXP.
Mm-hmm.
And so that's kind of our legacy. I was mentioning getting all of the good things that you need in a memory together in one. And so here you see, the four attributes of persistence, endurance, so that we have the ability to stand up to real memory workloads with the ability to write over and over without worrying about wear out.
Mm-hmm.
And the low latency performance for the RAM-like stuff, and then the reliability on top of that, to get into all of these very critical applications. And it's this kind of a combination of things that is very unique to MRAM, being able to provide them all in one device.
Question. I used to do satellite design at a company called Planet Labs, and one of the challenges we had is you would shoot a high voltage electrical, like what is it? You go to the cyclotron over in Davis, and you would actually shoot high, charged particles at the
high energy particles,
satellite.
yeah.
And the idea was you wanted to see what failed, and what consistently, went DOA on you was that the SSD that you'd launch into space, it would, if it got hit by the charged particle beam, it died and never stopped. It didn't even come back. It wasn't like a reset. It would just be permanently dead forever. And it's because the flash would like get corrupted or whatever, causing like serious boot issues with the firmware that'd be forever gone. Does MRAM have the ability to survive that kind of stuff?
Well, yes, it does. I mentioned earlier about storing the data in a magnetic state. It turns out that magnetic state is not disturbed typically by the types of radiation particles you encounter in space. So we have an inherent tolerance to radiation with MRAM technology, which is why aerospace companies have really picked this up. It started initially as a DARPA project with, if you remember the old Defense Research Agency that was funding things because of their interest in that. And it has now, for us, turned into a commercial technology. But aerospace is all over it. Starts with the airplanes. We're in most of the commercial airplanes that are flying today in one form or another, one system or another. And I would say some of the leading space exploration companies are using our MRAM in a pretty big way. And if you want true radiation hardened performance that you might need in deep space missions or in military applications, the part can be turned into rad hard, and we've licensed a couple partners to do that as well.
Okay.
So yeah, that's a good part of our legacy, and an excellent question.
Yeah, no, it was very hard to design to survive that, and it would kill a several $1 million satellite, right? If one random event. So it's pretty cool to hear there's a solution for that based on new technology.
Exactly. Yes. Yeah. So just taking a quick look at the product direction for us, we have been selling MRAM, as I mentioned, for more than a decade, and this PERSYST product line is what's in volume production today. And it's a RAM-like interface, but it might be parallel or serial, depending on your choice. But very fast performance, very high speeds of reads and writes, and that's been very successful for us in a number of applications. And going forward, we see an opportunity now as our density improves to get to a higher capacity point, 1 gigabit plus for us. And that way we can start being considered as a storage element as well. Whereas right now, we're used primarily as a data logging device or a buffer capture or something of that nature. We look to look more like a NOR flash replacement in time, but with very high performance. And not for this call, but just for listeners' interest, we are also very active in developing and optimizing the MRAM technology around AI models and AI needs out there in the marketplace. As you know what's going on there. You're very much a part of that. So that's kind of the lineup of things, and where we differentiate is in the writing, and it's really all about the writes for MRAM as regards to why we're better than other memories, and very high endurance, up in the 1E15, so trillions and trillions and trillions of writes in this PERSYST product line. And then you see the NOR flash and NAND flash typically down at maybe 10,000 to 100,000 writes. Now they're good for what they do. Obviously, NAND ubiquitous for storage, but where there's a write intensive workload, it's not standing up, and that's where MRAM fills in the voids here of what memory technologies can deliver typically. So that's what we've got going on there, and that's where we distinguish the PERSYST and the UNISYST. We have the RAM-like device, and then we've got the devices that are more of an enhanced NOR-like coming. That's on our roadmap.
I would also like to say, Well, I just wanted to interrupt. I would also like to say,
Yeah.
like, I think when you talk about write latency, there's also something called a page erase that you have to do with some of the flash
Yeah.
chips, and it can be very, very long. Like
It
write speed
can.
on flash is pretty fast, but the page erase takes forever. And so, like when you're writing megabytes of data, it actually can end up being very, very long, like seconds to actually, put that into memory to commit it.
That's a very good point. And the beauty of MRAM is that you can write a 1 or a 0, which means you don't really need to do any erasing at all.
Hmm.
And so we're ready to take the data as soon as you're ready to give it. And you don't run into the situation where you may have used up all of your erased blocks and then got to stop and pause, as you say, and then erase another block so you can write some more. That's just not the case with MRAM. So a huge software simplification there. And overhead reduction in terms of the time to write. So yeah, in addition to just how long it takes to actually physically write to the device, you don't have those kind of overhead things. NAND has similar issues, with large blocks of memory that have to get written or set up before you write. Yeah, that's another performance advantage for our MRAM. And just a couple more, just want to talk about applications a little bit. Avionics and transport we mentioned, but if you look at medical devices where patient monitoring is going on, automotive devices where there's all types of embedded systems around braking or charging or inverter motor controls that are also doing all kinds of monitoring, winning validation and casino gaming. Aerospace now is really taking off. Industrial controls is kind of the heart of our business, really, the whole industrial marketplace. And you can see just a number of types of applications that have really come to value the persistence and the endurance of MRAM. So this may be of interest to you too, talking about space. Turns out we're in a camera on Mars. And that was through a NASA design in the Perseverance program. We were designed into the Lucy mission to Jupiter. And here on Earth, we made some headway with some real high performance EVs, hypercar EVs that are really driving performance, and like some of the advantages of MRAM too. So just wanted to give you a little flavor of that. And I think with that, I can probably stop presenting and get into our conversation.
Yeah, no, thank you, Joe. I appreciate it.
Okay.
So for the audience, I'm Kwabena from OpenMV, and we make computer vision cameras. In particular, I wanted to talk about today a new little camera that we got called the OpenMV Cam. We're launching 2 new cameras. One of them is called the OpenMV Cam N6, and one is called the OpenMV Cam AE3. So the N6 is based on a new processor called the STM32N6 from ST. And so we've got this little guy right here. That's the processor. And in particular, it's got a great new feature, which is the ability to run AI models on a microcontroller. And we interface this with Octal SPI Flash currently, but we reached out to Everspin because we were interested in being able to interface these devices with Octal SPI MRAM, which Everspin offers. The benefit for both of our new camera modules, this is the OpenMV Cam AE3, so really, really small, 1 inch by 1 inch camera, is with Everspin's technology, all of a sudden you've got the way to read and write to a file system on board a 1 inch by 1 inch camera, and basically be able to save data to that camera very, very quickly. Let me get out the model that actually has Everspin's chip on it. Give me 1 second.
Very impressive that you knew which drawer to go to right away.
Yes, try to go with it. Here we go. So we've got Everspin's flash chip right there, and you can see when it's in focus, bada bing, bada boom.
There it is.
Yeah, so the idea for us was we're launching new AI cameras that have the ability to run AI models. And it's very exciting because this is the first time we're seeing NPU, neural processing units, available on the smallest low power systems possible. So with the OpenMV Cam AE3, for example, this little guy can run YOLO, which is an object detection model, at about 30 frames a second, and its power consumption is only about 0.25 watts of power. So at that low power consumption, you don't get hot. You're still getting 30 frames a second YOLO, though. So this means you can realistically track people moving around very quickly in an environment, track objects, track whatever you want. And then based on that, make inferences, send data, and then go back to sleep. And when you're in sleep mode, you're going to be below 1 milliwatt of power consumption. And so we're talking maybe 500, no, maybe like 300 microamps at 5 volts. And that's just of our current level of optimization. We hope to drive that down to less than 50 microamps or so. And when you get to those low power numbers when you're sleeping, all of a sudden this means you can have a battery life of years for such a system, which enables a whole new class of AI cameras that can be deployed anywhere and everywhere. And so we're launching based on 2 different architectures, the STM32 N6 and then the Aleph Ensemble. Both of them interface with Octal SPI flashes, and Everspin has a Octal SPI MRAM that is compatible, and we got working with both systems. So yeah, just tell me, Joe, a little bit about, like, you guys decided to make an Octal SPI MRAM. Actually, was AI something you were thinking about? Because it is an interesting package that not a lot of people are using just yet. It's very new, but I imagine there was some foresight here.
Yeah, the first thing we wanted to do, which you alluded to, was really to make it standard. So standard interface, standard packages, and compatible with things you're used to using, like NOR Flash. Although, bringing a lot more performance. And so that was the driving factor about, bringing Octal SPI to the forefront here, because even JEDEC has now standardized on that version of the SPI interface, which is very helpful. And in terms of what we were thinking about was, initially it started with the fact that even pre-AI, there's this need to do more software updates, feature additions, bug fixes, and that's all being done over the air, for a lot of these different systems that are out there now, particularly with what you just showed us. And so that over the air benefit there is giving the system guys an opportunity to update things more frequently. So the fact that we can write faster, we do it in a standard form factor, and it can look like Flash if they want it to, really lent itself to getting quickly adopted into these kinds of applications. And then to your point about AI, that's really emerged more recently, but it is very exciting. And because we have a memory that can do, various workloads, it can do the speed necessary, but also is persistent. We've got people, looking at how to use this now as for edge AI, or maybe endpoint devices in the extreme, at the very edge of the network, that would do the local AI processing, can now store model information for inferencing, and the ability to keep that persistently. So if you went off and did something else in the system, we don't lose the data, so it's always there. So good responsiveness. You talked about powering down also. We can power down standard low power modes for powering down. You can also turn it off, though. And the beauty of it is you can come back to where you were if you choose to set it up that way. So that quick recovery or boot up time that you could get because the data is there and available is also another attractiveness that people are latching onto.
Yeah, no, it makes me think about actually EEPROM, if you think. So, we have Flash on board our camera systems, but a lot of times folks want to have a small file system that they can write and log data to. And by default, we give folks access to a FAT file system that makes it easy. Gives you, because the OpenMV Cam is programmed in something called MicroPython, which gives you a very similar user interface that you would have on the desktop. And so you open a file in Python, and then you just write stuff to the file, and that could be like JSON structs or whatever. And then you would close the file and then reopen it, and et cetera. And so that would be your process for updating records. And this is quite a lot more flexible than, you know, having to deal with a fixed binary record size that has, you know, specific. Because you have more RAM, why make yourself suffer with crazy, you know, binary structs when you can just write out the data in human readable format, and just make it easier for your application programmers to do the job. The challenge, though, is when you're writing to flash devices, there is the erase time that you have to deal with. And when you're doing that, if power is lost, you have a high risk of corruption. Same for when you're writing to it. So, you know, MRAM has a really, it seems like there'll be a really nice opportunity here to like segment a part of the memory to be like act as an EEPROM, basically, where you can just perform single byte reads and writes and updates, and you can be guaranteed that that wouldn't, you know, your updates to that data log will not corrupt or destroy anything else if power was lost, and et cetera.
Yeah. So that's what you get with the products, you know, and that whole persistent catalog is all about byte level random access, reads and writes. So that fits in nice. One thing that customers are always asking for is a little more capacity. And so, you know, right now we've got a product line, the one we launched, which gets us up to about 128 megabits, not about exactly at 128 megabits.
Yeah.
And so they're saying, hey, I could use some more. And that's where the product on our roadmap now, the Unisys product that is this enhanced NOR function, you know, we plan to introduce that at 1 gigabit. And we think we can scale from there because, you know, we're at a point where we're using a commercially available process technology node to achieve that density. And we know that, you know, the whole industry is moving to scale down the nodes on MRAM as basically the memory of choice for non-volatile needs, where you have to do some writing, where there's you know, some type of write workload. So as those products become available for us towards the end of this year, as we sample, then you have even more benefit here with capacity to really consider your file system and file structure, along with, you know, the parametric data recording or just a capture of a snippet of data, or whatever you want to do.
No, that's awesome. And so I think moving into the next segment here, I actually wanted to show off the OpenMV Cam AE3 and show folks, you know, what we're talking about with the new revolution of AI microcontrollers. So you can see here, this is something called OpenMV IDE, and it is our desktop programming environment. And so I need to get a little bit farther away from the camera. Oh, no, this is working right now. And so what you can kind of see here is that the camera is tracking me as a person and finding me, and it's running at about 20 frames a second when it's streaming to the desktop environment. And then if I disable the frame buffer to reduce the load on the camera, we're actually at about 28 frames a second or so. And so this is running a YOLO V5 model on board, and we're pulling that off of the flash, actually, well, the MRAM on board. What we're doing is it has something called a neural processing unit made by ARM, the ARM Ethos U55. And so this offers about 200 gigaflops of neural network acceleration, well, 200 gigaops, int 8 multiplies. It's basically able to take a model that is stored in the MRAM off chip, and it pulls that, the MPU actually executes the model in place off of the MRAM using the Octal SPI bus, which runs at about 400 megabytes a second, 200 megabytes a second on this particular piece of hardware, but up to 400, or I think actually up to 500, right?
400 is the number, yeah.
Yeah, 400, but sometimes I see up to 500. People push to the bus speed a little bit higher.
Oh, yeah.
I don't think that's standard though, but anyway, still lets you get a very, very high speed. And, you know, pretty much your performance there is just dictated by how fast that MRAM can respond to commands and return the data to the MPU. And then the MPU is just going and inferencing and running the model more or less. What's crazy here though is that previous microcontrollers of yesteryear they're about 100x slower on doing this. So if we try to do the same thing on a Cortex M7 without an NPU, that's going to get about 0.3 frames a second. So one image every 3 seconds or so. Sometimes it's worse. Sometimes you can get it down to 0.06 FPS, which is like 1 frame every 20 seconds or something. It's crazy to speed up because, going from 0.3 FPS to 30, that is an 100x performance increase. And so all of a sudden it takes you from non-real time kind of, a demo, but, a proof of concept, I guess, that, hey, you could run a model on a microcontroller, but it's going to be too slow, to now it's real time. Now it's realistic. And this also comes with a 3x power reduction. So our previous systems, like with a Cortex M7, that was going to get you about, you'd be running at the 160, 180 milliampere range to run a model like that, run a model like YOLO. And now we're doing that at 60 milliamperes now at 5 volts. So, going from, 0.75 watts down to 0.25 watts. So, 3x less power and 30 and 100x more performance. So you're between 200x and 300x better than what you could previously do. And so it's really insane what this is going to unlock, the applications, the things you're going to be able to plug into. And it's not just YOLO, this is human body pose, face tracking, eye segmentation, object detection as we're doing YOLO, image segmentation. It's really whatever. I mean, you can even do depth, like you can do depth estimation using the camera. And it's not just also cameras. You also have IMUs. So you've got, accelerometer, gyroscope, microphone, and also time of flight distance sensor, whatever information you can think of. You now have a fast neural processing unit that's going to be able to churn through that and give you results. So what this means now in this future that, is here, that's here, not imaginary, but it's here, is that you're going to, be able to deploy AI anywhere. And now with Everspin's MRAM technology, you have the ability also to log data easily and be updating this, not just have the AI models flashed once in production, but be able to constantly update them and also have data logging happening at the same time on one device without too much worry that you're going to corrupt things.
Yeah, exactly.
Like what kind of things do you think we could do with this, Joe? With MRAM technology on a little camera like this?
Well, I think you've already gone through the things that are, top of the list there, but just thinking about,
images, saving images.
I was going to, yeah, exactly where I was headed. Yeah. I thought that if you wanted to get some snapshots or screen grabs or, a frame capture, you could write it to the MRAM and have it. Come back to it anytime you'd like to get to it. And it would happen very quickly. So you may not have somebody move out of the picture before you get the writing done, and so I think that would be a real attractive feature. And the ability to do that over and over, if you found that need because of the very high endurance numbers we support.
Oh yeah, well it's just a page erase. Ooh, we got some echo right there, but maybe that's me. I don't know. No, it's just a page erase really. Basically it comes down to if you actually try to save JPEG images every frame with non-MRAM technology, you can't run at more than like 1 FPS or so, because every time you want to save an image, if a massive page erase happen, then you save it, and then you get hit with another massive page erase. And so image might be several kilobytes, like for VGA, for example, that's going to be about 50 kilobytes or so. So plenty of, it's not like, 128 megabit MRAM can easily fit that. But if you wanted to keep a rolling buffer of, let's say, the last second or so of images, like, or et cetera, just the page erase speed, the page erase hit would be so high that you'd never be able to achieve any fast frame rate. And so with MRAM, you actually do have the ability to log data per image regularly. And you don't have to do that in memory when you go into low power mode or not. You can just do it in your main program and make the code easier. With a flash-based device, you're going to have to actually save everything in RAM and then only commit that when you go to sleep or so, when you're going in and out of low power modes versus constantly committing it to the actual memory directly.
Mhm. Yeah. Yeah. So just less movement of data is power savings too.
Yeah. Yeah. It's actually, yeah, it's really cool what this will be coming up to. I think though, you know, it's going to be a while before we see this in mass market though, because we need, well, we hope a lot of customers show up, you know, and start buying this to help reduce the price and get that down. You know, right now it's affordable for aerospace people, but we'd love to see it for all the commercial customers.
Exactly. Yeah.
Mhm.
So you know, volume scale will do that for us.
Yeah.
And what we're doing in the marketplace with discrete commercial MRAMs and what the foundries are doing with the development of this for embedded SoCs, you know, that wafer volume scaling and wafer tool efficiency improvements are coming. All of that is going to lead to you know, a cost benefit in time for us. And I mentioned how we get to some of the higher densities. That's not all just you know, like what it used to be with lithography scaling. There's a lot of device architecture, memory design architecture that's going into helping that scaling as well and getting to the higher densities. So, and we've really just begun. You know, the technology development that's going on now at 1x nanometer and below is really very exciting. So, yeah, hang in there with us. We'll go from you know, where we are today, which, you know, does attract a premium from a memory cost perspective relative to flash, but over time, I think all of these factors are going to come together and make this a very viable, high volume, low cost, and low power use of MRAM.
Yeah, no, we're excited for this future. So before we go, is there anything else you want to talk about, Joe? And I just want to give a plug for, you know, please check out the OpenMV Kickstarter for the OpenMV Cam N6 and AE3, and please back us on there. And Joe, what do you want to know? What do you want to let folks know about Everspin?
Yeah. Well, you know, we really enjoy working with folks like yourself, Kwabena, because what we know is that when we put this technology out there, people really figure out new ways to use it all the time. And so the use cases and the you know, the thousands of customers that we have now have all gotten very creative with their abilities. So hats off to you for what you put together and finding yet another unique use of MRAM. So thanks for that.
No, you're welcome. And we know we're glad to see and, you know, help support, you know, adding functionality for your chip. And we hope to see, you know, customers come up through with applications that can use it. All right.
Yeah.
Thank you, Joe.
Thank you.